Good morning.
Good morning.
I hope it was not too difficult to come today.
Just a little bit. Not as bad as 10.
So let's talk a bit about the schedule if you are concerned. We just did point 1. So we are behind one lecture. The schedule is comfortable. In fact, if you look at the bottom, the last week is empty. And the material is not too cramped. So I think we are going to manage very well. And we can even accept another snow day. I have a class that starts at 8, so that gets cancelled much more than this. And I survived that one too. So no homework due because we haven't covered the material. And today we'll finish week 1. And so the homework will be due next Monday. Is it reasonable? Yes?
Is that homework 1 and homework 2?
No. You have to turn in the homework of the things that I show you in class. That's common sense. I know some people don't have it. Some people in computer science have it less than people in other fields. Any other question? So relax, we'll do everything fine. I think you'll get your money worth of CS250. Furthermore, a lot of students tell me, I don't care about the material, I care about the grade. So the days off probably will improve the grade rather than sending it down. All right, so what did we do in lecture 1? We talk about a discrete structure that we call Boolean. This is a very simple structure because there are only 2 values, true and false. These are values that we attach to propositions, which are statements in English. And we combine a proposition with connectives. And we have a bunch of connectives. There are not too many. And we have tables that we call truth table to show how to combine a proposition using connective. This is very similar to the way in which you combine a number with operations. When you do 2 plus 3, you combine the 2 numbers with the operation plus. When you do true or false, you combine the 2 Boolean values with the operation or. We saw that we can apply this concept to programming. There is an example, particularly if you are a tester. Hopefully this will give you a little bit of motivation. We discussed a concept like a logical equivalence. Very loosely speaking, this is equality. Loosely speaking. We focus on one particular connective that we denote with an arrow. Sometimes we also write if P then Q. We have various names. We saw that this is equivalent to another form that we call contrapositive, which is this one. P implies a Q is equivalent to not Q implies a not P. Which makes perfectly sense, right? Because if P implies Q, if you have a not Q, you can't have P. Because otherwise you would have not Q and Q. You can't have both. There was not much more than this, right? We spoke a little bit about proofs. because proofs end up being a bunch of statements compounded by the connectives that we just discussed. We use what we call rules of inference. What is a rule of inference? It's an argument that is always true. And what is an argument? Well, it's a bunch of propositions with a conclusion, and the argument is valid if when all the propositions are true, the conclusion is true. How do we call this in normal life? Reasoning. The only really technical things here are the truth table and some terminology and equivalence about the implication, if that. Is there any question about this? I'm happy to answer any. All right, so after this, we move to the second section, which is about the sets. We gave an informal definition of set. And we said the set is a collection of elements. It's like a container where inside there are elements. We argue that the elements shouldn't be too crazy. It's a good thing if all the elements are all of the same type, like integers or students or elephants or whatever you like. In particular, sets that contain sets, and in particular a set that contains itself, we run in trouble. We have this last formula here that is a paradox called the Russell paradox that says that if we discuss whether or not a set contains itself, we run in trouble. And to make this precise is very difficult, but if the elements in the set are all of the same type, we are much better off. We learn about the notation, how we write a set. We learn about a crucial operation on sets that we call membership, or sometimes we say in. This operation takes one element in one set and returns either true or false. True if the element is in the set, and false otherwise. By checking over all the elements, we can know exactly what is in the set. And we have some notation. Is there any question about the notation? We will spend a lot of time on notation. It's not that there is much to understand. These are conventions. We know the convention, and when we write something, everyone understands what it is. A convention is like the side of the road when you drive. In the US, we are on the right, and in some other country, they go on the left. It's not that one is more right or more correct or smarter than the other. It's just an agreement. All right, so what we are going to see next are some operations on sets. And here I focus on two. One is the notion of subset or inclusion. We say when one set is included in the other, and the other is equality. Equality is related to the first. So what does it mean that A is a subset of B? Typically we write it in this way. If you want a little bit of intuition, if A is contained in B, A is smaller. Intuition, I'm just talking with my hand. And so smaller, we use the smaller sign. This is a smaller sign, but instead of having being pointed, is round. This may help you a little bit at the memory and the intuition. So if you have two sets, A and B, when do we say that A is contained in B? We consider all the elements. This A upside down stands for A, all. For all the element X, X is in A implies X is in B. Or if X is in A, then X is in B. So let's do an example. Suppose I have two sets. A is 1, 2, and 3, and B is 2, 3, and 4. Can you read it? All right. So, is A contained in B? Some people say no. Can we say in one sentence clearly, according to the definition, why A is not contained in B? Yes?
Each of the elements in A are only divisible.
All right. So, then I think what you want to say is, look, there is one element in A that is not in B. To be included, every element of A has to be in B. If there is one out, this invalidates the entire thing. And which element is in A and not in B? 1. Fantastic. Is B contained in A? No, for the same reason. 4 is in B but is not in A. Who can tell me a set that is contained in B? 2 and 3. If this were, then we can conclude that C, I'm running out of my pen, that C is contained in B. All right? Who can tell me other sets which are not so obvious? Sometimes we look at extreme cases because the extreme cases really give us the understanding. Yes? The empty set. Why? Because every element that is in the empty set is in B. Because there are none there, right? Very good, the empty set. Another extreme case. B itself. Why? Because every element that is in B is in B. Duh. Alright. So we understand inclusion or containing. We have a different notation for subset. The most general one is the one that I show you here. There is another one where there is a bar under. With this bar under, we say, look, they could be the same. Of course, so they could be the same also if we don't put the bar. If you want to say, look, one is containing the other, and they are not the same, and in this case we say that the containment is strict, or one is properly containing the other, then we emphasize this one by putting the bar, they say they could be equal, and then crossing out, they can't be equal. And so, in general, when we use this one, that says, look, we don't make it that hard. Is contained, could be equal, could not be not equal, we don't know. Yes?
Then why do you have the first two as, like, when would you use one or the other? If the third one means a proper.
You find this in textbooks. So, if you read another textbook, instead of this one, you may find this one, or instead of this one, you may find this one. So, I put them both. Yes?
So, for the purposes of this class, those are the same.
Say that again?
So, for the purposes of this class, those are the same.
Right. Yes. All right? So, notation plays a big role in math, so we have to understand. The second concept is when two sets are equal. And this is the definition. Let's take every x. X is in A if and only if x is in B. Or if x is in A, then x is in B. And if x is in B, then x is in A. And so this is equivalent to A, to this one, and the one with the arrow opposite. And so another way to say that A is equal to B is if A is contained in B and B is contained in A. Is a consequence. Straight from the definition. So far so good? Alright, so we learned two key operations on sets. containment and equality. And we know membership from over there. All right, so now there is another concept. I'll give it to you now, and this is just a curiosity. Later on, this will give us something very, very interesting. This is the notion of a power set. So let's look at the definition. If you have a set A, the power set of A contains all and only the subsets of A. So when is an element in the power set of A? If and only if is a subset of A. So let's take an A like this one, very simple, that contains 0 and 1. The power set, which is often written in this way, contains what? The empty set, because the empty set is a subset of A. The set that contains only 0. This is different from the element 0. This is a set that contains 0. The set that contains 1, and A itself. These are only and only the subset of A. There is no other. And so the set that contains this one is the power set of A. Yes?
So you consider null the power set of A?
Consider what?
Null.
No.
The null set. Would you consider that?
The empty set. Yes, we don't call it a null. We call it empty set, and it's this one. The definition is over there. All right. Sometimes some people, instead of writing this P of A, the power set is written 2 to the A. And you say, why that bizarre notation, 2 to the A? And so here there is a question. How many elements there are in the power set of A when there are n elements in A? Yes?
2 to the n.
Exactly. So, we denote more notation. If A is a set, A between bar is the cardinality or number of elements of a set. Cardinality or number of elements in A. And so, what is going to happen? Then the number of elements in the power set of A is equal to 2 to the number of elements in A. And this is why some people write it in that way. Later on we will see a number of other formulas which are similar to this. So as an exercise, you can try to compute the power set of a set that contains 3 elements, A, B, and C. How many elements there will be there? 8. Very good. All right, so now we look at a bunch of other operations on sets. These are operations where typically you have 2 sets and you combine them to get another set. Maybe you start to get a hang of this. You do it with number, you take 2 numbers and you combine them and you get another number with operations like addition, multiplication. Or you have booleans, true and false, and you combine the 2 booleans with operations like and, or, and you get another boolean. And so here we take 2 sets and we combine them with operations that we call intersection and union, and we get another set. So how is intersection defined? Let's try to read that formula there. So you'll this is the set of element X. The vertical bar says such that X is in A and X is in B. You with me? I'm sorry?
Or is
No. Intersection is an X. Yes, that's fine. I'm glad by any question. So, It's perfectly fine. And sometimes I fall asleep, so I may say it wrong, so I'm glad if people catch me. So if I have A and B, what is A intersection B? Two and three. So why 2 is there? Because according to the definition, x is in A and x is in B. So is it the intersection. Why 1 is not in the intersection? Is not in B. Why 9 is not in the intersection? Is not in B. It doesn't matter whether it is in both. It's not in B, so it's not in the intersection. Good enough? So the empty set is not, this is a great question. The empty set is not an element. When we talk about x there, x is an element. How do we understand that x is an element? How do we understand that this x is an element and not a set? Because we use that sign in. This sign x in A takes one element and one set. So x is an element of A. The empty set is not an element of A. Typically it's not. It's a subset of any other set. Very good. Yes. So union. The formula is very similar. Instead of asking for the element to be in both, we ask for the element to be in one. There is no harm if it is in both, because if it is in both, it's in one. And it's also in the other, but we don't care. It's in one. So let's go back to this example. What is A union B? 1, 2, 3, 4. Why 1 is there? Is in A. Why 2 is there? Is in B. Or is in A. It's also in both. But if we say is in both, maybe it is leading. Because we may give the impression that it has to be in both, right? When it really has to be in one. Why 7 is not there? Right, is in neither. Here, neither is important. We cannot say it's not in A, so it's not there. Why? 4 is not in A, and it's there. So here we have to say 7 is not there because it's in neither. Yes?
So for like existence, it's better to be like less specific, and then for negation, it's better to be more general.
Fantastic. Yes. Very good. For existence, the cheaper you are, the better it is. Because you have to focus really on what really matters. Very good. Very good point. All right, a complement. Complement is an operation that really works on two sets, but one is understood, so we don't mention it. The one understood is called the universe of this course. So we don't really know what is the universe in the example I'm toying with, but because there are numbers 1, 2, 3, we can think that the elements of this are the integers. The universe is the integer, right? And so the complements are all the elements that are in the universe except the one that are in the set I do the complement. So if I continue on my example, what is the complement of A? Suppose that the universe is a natural number, 0, 1, 2, 3, 4, forever. What is the complement?
You have 0 inclusive, and then anything above 3.
Right, so 0, 4, 5, 6, 7, ... You keep it going. 0, 4, 5, and so on. This is the complement. When it's infinite, we cannot really write all the elements. We put a dot, dot, dot. Later on, we will go to a lot of trouble to get rid of those dots, because those dots require some cooperation from the reader. And when the reader is a computer, getting the cooperation is hard. Complement. Next is difference. A difference B. And let's look at the definition. The definition this is the x such that x is in A and x is not in B. X has to be in the first, but cannot be in the second. Right? So, in this example, someone else, I want everyone to speak here. What is the difference? Has to be in the first, right? So we don't have many choices. Now you don't see it because the camera is not big enough, but A is 1, 2, 3. So it has to be in the first. So an element there can only be either 1, 2, or 3, because it has to be in A, right? But it cannot be in B. So what is the difference? 1. The set that contains only 1. Right? Why 1 is there? Because it's in A and is not in B. Why 2 is not there? It's in A and is also in B. And we can't afford that. Why 7 is not there? Because it's not in A. It's very good. Finally, the last one. Symmetric difference. We write it in this way. Let's look at the definition. X is in A. This is the exclusive OR. X is in B. When is that exclusive OR true? We have to go back to the lecture that we did the last time, and I can remind you, the exclusive OR is true if the two values are different. So one has to be true and the other has to be false, or you swap. And it's false when the values are equal. So what is the symmetric difference of my example? Again, A is 1, 2, 3 and B is 2, 3, 4. What is the symmetric difference?
1 and 4.
1 and 4, fantastic. Why 1 is there?
It's not in B.
Fantastic. Is in A and is not in B. Why 4 is there?
It's not in B, and it is in B.
Is not in A and is in B. Why 2 is not there?
Because it is in B and it is in B.
Is in both. Why 7 is not there? Neither. Is in neither. Alright? Alright, so we have this rule. These are not terribly difficult. So let's look again at the group of operations that we are discussing for sets. First, we look at membership. This is crucial. Membership takes one element in one set and is telling you whether that element is in the set. The answer is always yes or no. Then we compare sets, getting a Boolean result. We say whether one set is included in the other, or one set includes the other, depending on the order in which you want to look at it, or when two sets are equal. And so these are operations that takes two sets and return a Boolean. And finally, we look at combination of sets. We take two sets and produce another set. So far so good? You want to take the usual break? All right. Let's take 10 minutes.